So this is my first video regarding organic chemistry. I'm kind of going to go over the chapter 1 basics. You can see kind of the layout that I have here. I'm just going to go over some of the introductory topics and information about all these different things here. So formal charges, drawing the bond line structure, some tips and common mistakes that are often made when drawing these bond line structures, and atomic orbitals, so stuff like sp3 carbons, sp2, sp, and kind of differentiating between all these things. That's what we're going to do in today's video. So let's get started. So first things first, formal charge. You guys have probably seen it in your general chemistry classes. It's the same thing here. A good thing to note here I have written is that each line represents 2 electrons being shared. So I have this example right here. Each corner, and we'll get into this in drawing these bond line structures, but each corner of these bond line structures represents a different carbon. And that carbon has shared electrons between its hydrogens that aren't shown and between the other carbons that I have right here. For more complex atoms, you can count the number of electrons being shared. So if you have a nitrogen, if you have an oxygen, if you have a sulfur, those aren't as simple as carbons, who just have 4 bonds. So you really have to notice these lone pairs right here and notice that, well, you have 1 bond right here, 1 bond right here. If oxygen has 6 valence electrons and 4 of them are getting taken up, you're going to have some lone pairs, right? So we got that right there. And I have right here, for atoms that don't fill their bond, a formal charge needs to be added. So I have some examples right there. Some of these are going to come up when we're talking about the atomic orbitals. So whether this carbon is sp3 or sp2, that's a common thing that you'll see later on in organic chemistry, maybe your second organic chemistry when you talk about aromaticity. But yeah, so formal charges, I have this table right here to kind of keep track of how many bonds your atom has, which is very important in organic chemistry, identifying these formal charges, because when you get into chapter 2, mostly chapter 2, and talk about residence, keeping track of your formal charges will be vital for residence structures and throughout organic chemistry. So this table right here just shows how many bonds a typical atom should have. Specific ones are carbon, who should have 4 bonds, nitrogen 3 bonds, oxygen 2 bonds, and any of those halogens have 1 bond. And that says generally, because there are exceptions there. So an easy way to calculate formal charge, because sometimes if you're unsure, there is a manual way to calculate formal charge, is this right here. There's different ways to calculate this, but I think this is the easiest way. It's formal charge equals the number of valence electrons minus the sum of dots and the sum of bonds. And I'll get into some practice problems about that as well. There's different ways to calculate it, I know there is, but this was the easiest way for me when I was going through this class. Just the number of dots it has and the number of bonds. So I'll give an example right here. Let's say we have this structure right here. That's the bond line structure for this. If I wanted to draw all the atoms by themselves, we have something like this. Those 2 carbons on the end need to fill their octets. So there's imaginary hydrogens. If we look at this oxygen and trying to figure out its formal charge, we know that oxygen has 6 valence electrons. And we count up the number of dots. So first of all, let's do the things that we know. So we have the number of bonds. We know we have 2 for the number of bonds. And since it doesn't have a formal charge added to it, we know that it's going to be neutral. It's going to be 0. So it has to have 4 dots here. Whoops. So that would equal 0. So that's why that oxygen is neutral. It doesn't have a plus or minus added to it, because if you calculate formal charge, it's easy to see. So that's formal charge. Let's talk about how I know how to draw those bond line structures, which is very crucial in organic chemistry. You guys will get the hang of it very fast. A couple things to note here. If you hear the term carbon skeleton, that's the same thing as saying a bond line structure. If they're single bonds, they're often in a zigzag format. So if you have, let's just say a row of carbons, let me fill in the hydrogens as well. All right, we have this row of carbons. There's 3 carbons. You want to show them in a zigzag way. So you want them to zigzag if they're single bonds. I have this example right here. So this shows, if I want to count all of the carbons, 1, 2, 3, 4, 5, 6, and 7 carbons. Let's see if that adds up here. So we have 1, 2, 3, 4, 5, 6, 7. So for these carbon skeletons, it's going to show up the exact same way in these bond line structures. Double bonds are shown the same exact way as you would in a Lewis structure. It's just shown with 2 lines. Often you will see, or I guess you won't see something like this. That's not really shown. You have to show this little gap right here. Same thing with triple bonds, as I'll get to right here. A thing to note here, we talked about zigzags with the single bonds of carbons, but since triple bonds have a linear geometry, you can't really zigzag with them. They have to be shown in a linear fashion, as it's shown right here. It doesn't just go like this. You can see it kind of stops and is just linear right here. So for triple bonds, for these bond line structures, you really want to make sure that whatever you do, you stop it. So let's say we zigzag. Let me show a different orientation. Let's say we zigzag this way, and this is our triple bond. We want to show these carbons being linear. And we have those next carbons coming out. All right. Moving on to the hydrogens in bond line formations. You can see when I've been going through all these structures that when we look at our bond line equivalents of them, that you don't see any hydrogens for these carbon skeletons. And that's because we do not show them when they're connected to carbons. You don't show the hydrogens when they're connected to carbons, but when you show them to other atoms that are not named carbon, you do show them. So for nitrogen, oxygen, sulfur, if you have a halogen that has a hydrogen attached to it, you show that as well. So anything that's not a carbon, you show in your bond line structure, and that's what's shown here. You can see in blue, we have all of our hydrogens. So a good way to determine the number of hydrogens is to remember that carbon has 4 bonds. So you look at how many lines are shown to the specific carbon, and if it doesn't have a formal charge, then you know how many hydrogens to add to it. So that's what I wrote right here. You can see in this example, there are 2 bonds shown to this specific carbon. And since it is not a plus or minus, it doesn't have any formal charge, it's neutral, its formal charge is 0, then you can kind of guess that it has 2 hydrogens attached to it, because we know that carbon needs 4 bonds to occupy its octet rule. So there are 2 imaginary, not really imaginary, but there's 2 unshown hydrogens right there. Okay. So that's about drawing bond line structures, and some tips and common mistakes that you'll see that, kind of stuff you want to avoid is that some tips that are shown right here is that for the zigzags, you can show them in any orientation. So it doesn't matter if you have it starting like this of a zigzag or if you have it starting like this. It means the same thing. You just want, as it's shown right here, you want those bonds as far apart as possible. So you don't want a zigzag to be shown like this. Obviously, that would be still correct, but it's better to show them as far away as possible. So for double bonds especially, you don't want to show this double bond kind of in here. You want it as far away from the other bonds as possible. And that's the same thing that I wrote right here. So this bond coming out here is not shown like this. Do not do that. You want it as far away from these bonds as possible. And then another mistake is to, when you're writing bond line structures, don't include, if it's not an oxygen or a nitrogen, if it's just a carbon and hydrogens, you don't want to include them in your bond line structures. It's just the lines. It's just the lines. All right. Last thing before some practice problems are these atomic orbitals. So you guys have definitely seen these in your general chemistry classes, but you have to know what the atomic orbitals are to go through organic chemistry. So we have sp3, sp2, and sp. Let's focus on sp3. So any single bond that you have is going to be an sp3 carbon, or sp3 any molecule. So you have a carbon attached to anything. I wrote right here that R, you'll see a lot in this course, means any molecule. So when you have a carbon single bonded attached to any molecule, and let's say we have, its hydrogens attached as well, that is going to be an sp3 carbon. Okay. For sp2 carbons, you can think of that 2 being a double. So sp2 is for double bonds. So if a carbon is attached to another carbon, or if a carbon is attached to an oxygen and it's a double bond, that is an sp2 carbon for both of these carbons. And this oxygen is also sp2 because it has a double bond connected to an sp2 carbon. Okay, some other sp2 structures that are kind of minute that you'll get into if it's not just a double bond. There are some exceptions. So if a nitrogen has 3 bonds and 2 lone pairs, that is an sp2 nitrogen. If a sulfur has 2 bonds and 4 lone pairs, that's an sp2 sulfur. And if a carbon does not have a filled octet, if it only has, let me redraw this, if it only has 2 bonds and it has a lone pair and it's missing something else right here, so it gets a negative 1 for its formal charge, then that is an sp2 as well. Okay. sp is really simple, any triple bond. So if you have a carbon triple bonded, let's say to a nitrogen, that is an sp carbon, and that is an sp nitrogen. Another exception that I wrote here is that if you have a carbon that has a filled octet, it has a double bond on the left side, a double bond on the right side, it has a filled octet, that carbon in the middle is also sp. So even though that's not a triple bond, if it's in the middle of 2 other double bonds, that's an sp carbon. And let me give a quick example. Let's say we have something like this. This would be shown as, let's see here. Yeah, let me put that hydrogen a little lower to make it make a little bit more sense. So identifying the atomic orbitals on this, I already said that this would be sp, but don't think that these 2 on the ends, these 2 carbons on the ends are also sp. Those are just sp2, right? They're just normal double bonds. The only one that differs from all these rules is this one in the middle. That's sp. Okay. So let's get into some practice problems. All right. Let's identify the formal charges on for each of these. So obviously I have a lot of practice problems here and we're going to go through them. So we know that we don't really have to focus on these hydrogens because they have, we know that they only need one bond, so these hydrogens will all have a 0 for all of them. So let's just focus on this oxygen. And again, formal charge equals the number of valence electrons minus the number of dots that it has plus the number of bonds that it has, okay? So for this formal charge, oxygen has 6 valence electrons minus the number of dots, that's 2, plus the number of bonds, that's 3. So that would be 5 minus, or 6 minus 5, that would be plus 1. So this oxygen would have a plus charge, just a plus 1. Typically in organic chemistry, you wouldn't show it as plus 1 charge, it would just be plus. Okay, so we got that one done. Let's focus on this next one. Again, for these hydrogens, we don't really have to worry about them. We know that, they are going to be 0 because they have one bond attached to them. So that's not too hard. These carbons, we just want to look if they have 4 bonds, which they do. So these carbons would be 0 for the formal charge as well. But let's focus on this nitrogen, right? It has 2 lone pairs. It has 2 bonds. So to calculate the formal charge quick, it has 5 valence electrons minus number of dots. It has 4 dots plus 2 bonds would be 6. 5 minus 6 would be negative 1. So there's a couple ways to do this. If you remember that nitrogen to fill its octet needs 3 bonds, then you know if it's losing 1 bond, if it only has 2 bonds, then you know it has to be some type of unfilled octet. It either has to be a plus or a minus. And in this case, the formal charge would be a -1. So this nitrogen would have that charge, okay? Let's focus on this oxygen here. And why I'm only focusing on that, you might ask, because this carbon has 1, 2, 3, and a 4th bond here. That carbon has 4 bonds. We know that if a carbon has 4 bonds, its octet is filled. So that doesn't have a formal charge, but this oxygen might, right? Oxygen likes to have 2 bonds to fill its octet. So let's calculate that formal charge on oxygen. We know it has 6 valence electrons. It has 2 dots and 3 bonds. So that's 5. So 6 minus 5, that oxygen has a +1 formal charge. +1. Okay. This carbon right here is something a little bit different. It doesn't have 4 bonds, it has 3 bonds and 2 lone pairs. So right away, we went through this problem before, that has a -1 formal charge. Again, 4 valence electrons, it has 3 bonds and 2 dots. That's a -1 formal charge. All right. Moving on, this question asks to draw the structure for each of the following ions. In each case, identify which atom possesses the formal charge. Okay, so we have boron, and we have 4 hydrogens with a -1 formal charge. So this goes back to kind of Lewis structures and recognizing on the periodic table, what does boron show? We know that boron is in that group right to the left of carbon if you're looking at a periodic table. So we know it only needs 3 bonds, but this one has 4, and that negative charge would show up on that boron. Our hydrogens are all good. They all have 1 bond attached to it, so their octets are filled, but that boron is exceeding its octet, right? All right, for this next one, we have nitrogen with 2 hydrogens. So this is not filling the nitrogen's octet because remember, nitrogen wants 3 bonds. This one only has 2. So that means that nitrogen has to have a -1 formal charge. Okay. This next one we have C2H5 plus. So 2 carbons, 1, 2, 3 hydrogens, 1, 2. That makes it 5 hydrogens. This carbon right here only has 1, 2, 3 bonds. So it has 2 dots right there, 1 lone pair. So I would have a plus for the formal charge, and that's why there's an ion right there. Okay. This next question is getting into identifying and drawing these bond line structures. So the question asks, for each of the following molecules, determine the number of carbon atoms present, and then determine the number of hydrogen atoms connected to each carbon atom. All right, let's get started. So let's focus on A right here. Number of carbons, we look at the zigzag pattern. All right, so we know there has to be a carbon at the end there, makes it 1. This has to be a carbon. There's another corner right here. There's a carbon right here, and a carbon at the 2 ends. So counting those up, we have 1, 2, 3, 4, 5, 6 carbons. And I guess the difficult part is understanding how many hydrogens there are. So this carbon, and again, you'll get really good at this when you go through this class. And let me, count up these hydrogens. So this carbon at the end only has 1 bond. This whole molecule doesn't have any formal charge. So we know it's all of its carbons octets are filled. So it has 3 hydrogens at the end to fill its octet. This carbon right here has 2 bonds. So it means there has to be 2 other bonds. So there's 2 hydrogens. Same thing for this carbon, 2 more hydrogens. This carbon in the middle right here has 3 bonds. It's attached to 3 other different carbons. So it only needs 1 other hydrogen. And we have 2 carbons at the end with only 1 bond. So it needs 3 hydrogens at the end. Okay. So let's count all these up. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogens, and 1, 2, 3, 4, 5, 6 carbons. Okay. There we go. I'm not going to do this one. That's another just carbons and hydrogens. Let's focus on one which has, an oxygen attached to it, stuff like that. So for this one, we have a carbon right there. Let's focus on another corner. We have a carbon right there, and it goes all the way around. So we have 1, 2, 3, 4, 5, 6 carbons. All right. Again, no formal charge is attached to this. Our oxygen has 2 bonds, which it likes. And that means that all of our carbons need to have filled octets as well. So let's focus on this carbon right here. Does it have any hydrogens? It has 1, 2, 3, 4 bonds, so it has no hydrogens attached to that one. All right, this carbon right here, it has 1, 2, 3 bonds, so it needs 1 more hydrogen. Same thing for this one, it has 1, 2, 3 bonds, so it needs another hydrogen. This one just has 2 bonds, right? It's not connected to any double bonds, it just has 2 different carbons on each side of it. So this has 2 hydrogens as well. And same thing for these other 2. Okay. So counting up these hydrogens, we have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. Hopefully that makes sense. This one is a structure or an orientation of a structure that you'll see later on in this course when you talk about conformations and get into that kind of stuff. But it just means the same thing. We have a carbon, it's kind of zigzagged like this. So we have a carbon at the tip of there. This is another zigzag, this is another zigzag, and we have 2 at the corners on each side. So in total, there are 1, 2, 3, 4, 5, 6, 7 carbons. All right, counting up the number of hydrogens, we don't have any double bonds or triple bonds. It's all just single bonds. So this has 2 bonds attached to it, so it needs 2 hydrogens. This has 3 bonds, so it needs 1 hydrogen. This has 2 bonds, so it needs 2 hydrogens. Same thing for this one. This has 3 bonds, so it needs 1 hydrogen. And these ones at the end are the same as the other end. They both have 2 bonds, so they need 2 hydrogens. So counting up the hydrogens, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Alrighty, a lot of counting. All right. This is getting into atomic orbitals. So talking about, is it sp, sp2, sp3 carbons? So let's remember that sp3 is single bonds, sp2 is double, and sp is triple. So let's go through this molecule and identify what kind of hybridization each carbon atom would have. Let's focus on this one first. You can see that all of its bonds are just single bonds, so this one would be sp3. This carbon, again, sp3, it only has single bonds attached to it. This one, though, has a double bond. And I don't want you to think about, oh, it's attached to a double bond, but it's also attached to a single bond with this hydrogen. And it's also attached to a single bond with this other carbon. No, if it's attached to one double bond, even though it might have other single bonds, it's primarily attached to this double bond right here. So this is an sp2 hybridization. Same thing with this one, sp2. This carbon is close to this triple bond and it's close to this double bond, but its primary bonds are right here. All right. So this is just sp3, right? These 2 carbons are both contributing in a triple bond with each other. So both those carbons are sp, hybridized carbons. All right. That one was pretty straightforward. This one asks to determine the hybridization state of each carbon atom in each of the following compounds. So let's go and do that. This carbon right here, sp3, it's attached to all single bonds. This carbon right here has single bonds on this side, but it also has a double bond with that oxygen. So that carbon is sp2. And if we were to label this oxygen, that would also be an sp2 oxygen as well. And these 2 are both participating in a double bond, so those 2 carbons are sp2. All right, this next structure, we have a triple bond that should signal that that is, both those carbons are sp carbons. All right. And then every other carbon, there's no magic here. They're all sp3. They all have single bonds, singular bonds in their octets. The only difference is this triple bonded carbon-to-carbon triple bond is sp. This one right here, we have a double bond, which should signal sp2, and then we have single bonds here. So we have a double bond. That double bond is sp2, and these 2 carbons are sp3. They have single bonded octets. All right. And that is all I got for you guys. So if you like this video, give it a thumbs up. I plan to record more practice problems, one video that's just primarily focused on practice problems throughout this chapter, and after that video where I go through a bunch of practice problems on these topics, if I didn't go through enough already, I will go through chapter 2, and I'm getting all these problems from the Klein Organic Chemistry 1 book, so if you want to follow along, that's the textbooks I'm going through. So thank you for watching. I'll see you in the next one.